Okay, hello everyone. Today we are very happy to have Eric Mintun from the University of British Columbia, and he will talk about non-local multitraces and relations to conformal field theories. So please take it away.
All right. Well, thank you for having me and then inviting me through the internet to speak to you guys. So this is a paper that I've worked on with Felix and Jason and Mark Van Ramsdonk here at University of British Columbia and Anthony Speranza out at Perimeter Institute. The title is a mouthful, but the idea is actually probably simpler than the title would suggest. What we're looking to study is really the entanglement entropy properties of a set of CFT states that are constructed by inserting perturbative non-local sources in the Euclidean path integral. And that's the description of the project is shorter than the title of the project. Although you might ask why I would be interested in this sort of state, which is a reasonable question. And so Euclidean is interesting because by putting sources in the Euclidean path integral, we're building states of the original theory, whereas if you put them on the in the real-time evolution, you're deforming the CFT to a different CFT or not to a CFT. And additionally, by doing a little bit of Euclidean evolution, you're guaranteeing that you're building kind of a nice finite energy state that's well-defined. Perturbative is useful because, of course, it's good to have perturbative control over things. Many entanglement entropy quantities are easier to calculate when we have this perturbative control. And in particular, we're going to be interested in, I guess, a program that's been referred to as geometry from entanglement, or this idea that I'll get into a little bit more later, that you can actually show that starting from the Ryu-Takayanagi equations for perturbed states, for states that are perturbations of the vacuum, that you can recover the linearized Einstein's equations in the bulk. And trying to kind of make more progress in that direction is one of the motivations of studying these states. And then finally, maybe the most unusual thing in this description is that we're studying non-local sources as opposed to local sources. And it turns out that this is because non-local sources are better for studying the entanglement entropies, not of the CFT states, but of the bulk fields in the ADS-CFT dual. And we're kind of interested in an explicit checks or use of the Fokker-Lukowitz-Maldacena formula, which includes a bulk entanglement correction to Ryu-Takayanagi. And so having a tool that kind of is better for the entanglement entropy of bulk fields on top of the ADS background is a valuable thing. And I'll get to in just a couple of slides why these non-local sources are better for these bulk fields. These bulk entanglement entropies. So just one more little bit of motivation on this geometry from entanglement program. The perturbative Ryu-Takayanagi equation and its FLM extension. And here by perturbative, I just mean we are doing it for some state near the vacuum and then subtracting off the vacuum version of the equation. So all of the entanglement entropy and area quantities are differences from the vacuum values. These imply the linearized Einstein's equations in the bulk. And this was shown a while ago by these people. And there have been many extensions since then. It's been extended to be linearized around other backgrounds than vacuum ADS. It's been extended to second order linearized Einstein's equations to include higher derivative corrections in the gravitational theory than just beyond just the regular Einstein's equations. It's been extended to include semiclassical corrections, kind of one order down in N. And these come from, these require that you use the FLM extension to RT. And what we're really interested in, this argument, I guess, that was done by Swingle and Van Ramsdonk is rather abstract. And so we were interested in seeing if we could get more explicit results for that. if we could maybe push it farther to second order semiclassical results. And what would be really great would be if we could start to go kind of beyond the semiclassical or semiclassical gravity and kind of see perturbative quantum gravity correction. So when I get to that part of the talk, when I get to that part in the talk, I'll kind of maybe talk about these things a little bit more in depth, but at the moment it's just a motivation.
So what do you mean in particular by the perturbative quantum gravity results?
What we were hoping to get, I guess the second thing I should say is that we did not succeed at this. So maybe part of the problem is that what we're after is not very well defined. But the semiclassical results are classical Einstein's equations equal to the expectation value of some quantum stress tensor. And what we were hoping was to be able to get maybe in some perturbative kind of order by order sense where the equations are corrected by some expectation value of some quantum object associated with perturbations of the metric, as opposed to just what was done kind of previously, which involves like expectation values of quantum scalar fields on the bulk in the bulk. One of the things we got hung up on is that it's possible that this is simply not very well defined, and we were hoping that through all of this we could get a better definition, and I'm not entirely sure we succeeded. So I'll talk a little bit more about it, I guess, towards the very end if we have time. But yeah. So that was a brief introduction. The order of business, I'm going to go through a bunch of preliminaries, actually define the states that I'm talking about, and set up some stuff to talk about them more in depth. And then be interested in the entanglement entropy to leading order and then the subleading order in N in these non-local sourced states. And then finally talk about some of this gravity equations from RT and from FLM. All right, so as a review, a pretty common thing to do in CFT is to construct the vacuum state by evolving with the Euclidean path integral. The idea is you evolve up to Euclidean times 0 out from infinity, and you set at that boundary at 0 arbitrary boundary conditions on the field, and what you get is a wave functional as a function of those boundary conditions for the vacuum of the state. And the basic idea is that the Euclidean action being run for an infinite amount of time suppresses every energy except the ground state, and so you pick up only the vacuum. If we want excited states, all we need to do is perturb or deform the Euclidean path integral to have these local sources, sourced by lambda, with really any operator you want in here. Although we're going to be assuming for the whole talk that lambda is perturbative and O is light and single trace. And so this will give you the wave functional for various excited states of the CFT. It's been shown that these states constructed this way map one-to-one with bulk coherent states or coherent states in the ADS bulk. And so since O is single trace, it maps to some fundamental field in the bulk. And to leading order in N, the argument is basically that one insertion of an O corresponds to a single particle state in the bulk, and then exponentiating that O just exponentiates the single particle state. They don't interact with each other at leading order in N, so you get the coherent state. Coherent states form an overcomplete basis, so you might wonder why bother with these non-local sources that I'm about to talk about. And it turns out that coherent states have a problem in this case, which is that they can always be written for any division into a region and its complement. A coherent state can be written as a unitary acting on the region times a unitary acting on the complement times the vacuum. And that means that all of these coherent states have the same entanglement entropy as the vacuum for any region that you might want to divide the bulk up into. And so they don't make a very good probe of FLM for that reason.
So sorry, are you saying that they are the product states in the bulk? Is it what you're saying?
They are product states. No, because the vacuum is not a product state. They are. It's not that they don't have bulk entanglement entropy. They don't have different bulk entanglement entropy than the vacuum. And so, in this regime where we kind of are measuring everything vacuum subtracted, they don't tell you anything.
Okay. Yeah. Thanks.
I guess a quick way to see this is that you can take the coherent state and apply the Bogoliubov transformation. And then in the exponent, it's just operators acting on the left plus operators acting on the right. And that divides into a unitary on the left and a unitary on the right. And then just applying a unitary to one of the regions and not mixing them together doesn't change the entanglement entropy. So the entanglement entropy is the same as the vacuum.
Well, I mean, I'm still kind of puzzled about it. But maybe I'm just gonna mention. Maybe it's obvious. I mean, like you seem to imply that it's obvious, but this is an exponent in momentum space in the bulk, right? So in real space in the bulk, like this is a very, I mean, in principle, a complicated object, right? So.
I mean, sorry. What they've shown is that these states correspond to in real-time evolution coherent states. So I guess I don't see what the confusion is, but
yeah, let's move on, and maybe I can come back to this towards the end.
Right. And so to get non-trivial bulk entanglement entropy, by which I mean different than the vacuum, we can use the same construction with non-local Euclidean sources. And the basic idea is to do the same sort of deformation, except instead of this lambda O, it's lambda as a function of several locations times many light single trace operators at different locations. For most of this, because I'll be working with multi-trace operators or non-local operators with any number of insertions. But it's worth mentioning that bilocal sources are special in the sense that they correspond to Gaussian bulk states. And since Gaussian states are still potentially tractable, bilocal sources specifically might be useful for explicit calculations. All right. So I've been talking about states, but when we go to calculate an entanglement entropy, what we're really going to need is a density matrix. It's fairly easy to construct the density matrix from the state. You just take another copy of it. You put it on top. You kind of flip it upside down, put it on top, and then sum over the complement of the region that you're interested in. And what you end up with is a different path integral with two boundaries now, one on the underside of the region you're interested in and one on the upper side. And you just integrate around between those two boundary conditions. And to simplify things, we're going to simplify to real lambda and real operators O. And we can think of this as a single W of O with support on the entirety of tau instead of just on the negative tau. With one caveat that I'll talk about now. Which is that not all sources are possible with this construction. It's not possible to have a non-local source that simultaneously has support on tau greater than 0 and tau less than 0. Because I originally set up the system to be non-local sources in the state, and the state only lives on the lower hemisphere or the upper hemisphere. But with a little bit of a modification, we can get these sources as well. And the idea is to assume that you have a second CFT. So you now have two disconnected CFTs and a source that couples not two locations in the same CFT, but across the CFTs, as I've drawn here. And then if you trace out an entire CFT, you get an effective source in the remaining one that corresponds to a source that runs across, propagates through the CFT you've trained out, you've traced out, and then comes back through another source on the other side. And so what this does is it gives you an effective source that couples the lower part to the upper part. It's written here, but from here on out, I'm just going to assume that we can have couplings that couple the top to the bottom without going through this whole process. And it's worth pointing out that because we've accomplished this by tracing out a second CFT, it's possible that, if I took one CFT and I consider the entanglement entropy of the entire spatial slice, States constructed this way with perturbative sources inserted on the vacuum could only give you 0 entanglement entropy because they're pure states. But when I couple the top to the bottom like this, because I'm kind of implicitly tracing out this second CFT, you will be able to get non-trivial entanglement entropy for the entire region. So the CFT with these sorts of couplings is in a mixed state. For a quick aside, I want to talk about the Inscaling real quick of these things. There's a question of, we want the sources to be perturbative, but kind of how big can we make them in N? If I choose to normalize the operators to be N to the 0, so they're something like, they're single trace operators, they're like going to be normalized as 1 over N trace of whatever their trace of. Then their connected 2-point functions fall off. Oh, there's an error here. This center one should be N to the -4. But their connected endpoint functions fall off, and higher endpoint functions fall off in N. So with this normalization, the action itself is order N squared. Our perturbation can't be bigger than the action if we want the perturbation to make any sense. And so the largest we can possibly take lambda, regardless of how many operators lambda is multiplied by, is going to be some small number times N squared. So from here on out, this is the normalization I'm going to use. The lambdas are going to be assumed to go as N squared, and the O's are going to be assumed to go like this, and their correlators will fall off in N. We're going to be calculating entanglement entropies. And so I just review 2 quick things about entanglement entropies. One is that there's a conformal, well, okay. We're going to be calculating entanglement entropies of ball-shaped regions. And in particular, there's a conformal transformation that takes any ball-shaped region you might want and maps it to a cylinder or to a sheet where the boundaries of the boundaries of the original path integral are at like t equals 0 and t equals 2 pi. And so this essentially maps the problem that we're talking to into something where the vacuum density matrix is the thermal, or sorry, the vacuum's a dangerous word. The unperturbed density matrix is a thermal density matrix. And so I'm going to be using off and on the fact that the unperturbed density matrix is thermal because of the ability to do this mapping. Second, a typical way to calculate the entanglement entropy is via the replica trick. So the original kind of definition of the entanglement entropy can be rewritten as this derivative as the replica number goes to 1 of log of the trace of n rows all multiplied together. This trace rho n has two parts. It has Zn, which is going to be this same partition, the same path integral, but on n copies of the system all kind of attached together, one after another. And then there's a normalization that consists of the original normalization of the density matrix of the replica 1 density matrix raised to the power n. So these two terms will eventually be important. And the second one, the Z1 is calculated just by doing the path integral on the original sphere that I showed on a slide or two back. So we can take this trace rho to the n and interpret it as the thermal expectation value of an operator given by our source, e to the WO, where this is now the n replicated W in the thermal state. And then we can expand that to any desired order in the sources. And so schematically, you know, there might be some ridiculous large term in lambda in trace rho to the n. This particular one I picked out is going to be 8 different lambdas, and you know it's going to involve, after doing this expansion, an 11-point function in the thermal state. Furthermore, we can then consider connected and disconnected correlators of this 11-point function, and the disconnected correlators are going to be lower order and 1 over n, and so they're going to be more dominant. And so, for example, this particular choice I picked out here is going to be order n squared, this particular case. And also, we're going to assume that for these operators in the thermal state, their one-point functions are 0. Okay, so this setup suggests, or a diagrammatic expansion of this construction is quite useful, actually. In particular, there are 2 types of vertices. One that corresponds to the source itself, which would be going to be this red dot with a dashed line. So we'll have that connected to any number of operators, because we are sourcing non-local sources with any number of kind of non-local insertions. And then there's a second vertex that's associated with the correlators, or the connected correlators. So the blue dot with solid line is going to correspond to 2-point functions or 3-point functions or 4-point functions. And we can build up diagrams associated with the things on the previous slide by building diagrams that just alternate blue-red connections. So for example, a particular contribution to that same thing I showed 2 slides ago would be this particular diagram. And what I want to argue now is that contributions to the entanglement entropy that go as n squared map kind of one-to-one to tree diagrams in this diagrammatic expansion. And it's fairly straightforward to make this argument just by induction. We can start with the minimum tree, which just by counting, it goes as n squared. The correlator is n to the -2, and each of the sources is n squared. If we extend the tree by connecting to a red node, we necessarily added at least 1 red node and at least 1 2-point correlator, so we've added nothing, so it stays n squared. If we add something to a blue node, we've added necessarily 1 source, but we've turned this 2-point correlator into a 3-point correlator, so it's lower in n, and we added n squared, so this is also n to the 0. On the other hand, if we add a loop by using a dashed line, we necessarily remove 1 source, and so this is 1 lower order. This is 1 n squared lower, and so these loop diagrams are not n squared; they're n to the 0. And finally, we can try to extend, or we can try to form a loop by taking 2 correlators that were disconnected and considering their connected component instead. This also forms loops, but it's also lower order in n by the same scaling that I was talking about earlier. So tree-level diagrams correspond to n squared contributions to the entanglement entropy. And so if we want to talk...
One second, maybe I guess I missed that, but I think you assume 1 operator O as the source, not more.
Sorry, what?
You assume 1 operator O as the source and maybe copies of it, but not different operators.
Yeah, for simplicity, yes. That's not, I mean, I guess what I'm saying here, yes, but you can put indices on the lambdas and on the O's, and it becomes harder to keep track of, but in principle, it all works out the same way. But yeah, everything I'm writing here, we're kind of assuming there's just 1 operator I'm interested in. For simplicity, it's associated with the scalar field in the bulk. But I think everything should work out for things that have spin or many different types of operators. But yes, there is no index that scales as n. So it's not as if a loop in here introduces a factor of n that comes with the loop, the way it would in like a double line notation that we're more used to in ADS-CFT. All right, so studying order n squared entanglement entropy means studying trees, or in this diagrammatic expansion. So I'm going to start by talking about a very specific example, or a specific case, which is consider the region that we're interested in to be the entire CFT. So in this case, the path integral for the density matrix becomes disconnected into the part that is less than tau equals 0, and the part that's greater than tau equals 0. when we do the replica trick will fuse the top half of one density matrix to the lower half of the next density matrix, and so on and so on. And these pieces are all still disconnected. They're kind of connected sideways, but they're kind of disconnected pieces still. Now, non-local sources connect within a density matrix, and so they connect across like this, while correlators run along the thing that you're running the path integral on. So they connect across the directions that have been fused in multiplying the rows together. So a tree diagram on these kind of disconnected case would look something like this. For any tree that we might build this way, in the normalization, the other term that shows up in the entanglement entropy, you can build an equivalent tree on just one sheet that matches this other tree exactly. And so, because in the entanglement entropy, these two terms subtract, these two trees will cancel out. And what you will get is that you will have no contribution to the entanglement entropy at order n squared from these sorts of diagrams. And in particular, because these non-local sources that connect.
Sorry, a question like order n squared means like basically the order of the gravity dual itself, right? And like the classical fields in the bulk.
Right.
Yeah. Okay.
Yeah. So I mean, right. So I mean, so I guess what am I trying to say? For a local source, in a case where I was not looking at the whole CFT, you do get order n squared entanglement in the CFT, which corresponds to some kind of perturbative change in the area in the bulk. Here, because we're looking at the entire CFT, a perturbative local source cannot possibly create entanglement entropy because the thing's just a pure state. Okay. And what we're saying here now is that these non-local sources are actually also failing to do that, even though you might think naively from what I said earlier that you could succeed at that. And I guess to say something that's maybe a little, well, maybe it's a little bit more surprising, or maybe isn't. These couplings that go from the lower half to the upper half corresponded originally to things where I traced out an entire second CFT and the couplings that connected you from one CFT to that CFT that I traced out. And so what this is essentially saying is that it's not possible to use these states to build n squared entanglement between two separate CFTs. All right, so that's a very specific case. But we can say something stronger, which is that for these non-local sources, no matter what we add, we can go find a set of local sources that at leading order give the same entanglement entropy for any region. And this statement includes the one of the previous case, because again, local sources couldn't possibly create entanglement when they're creating pure states on the entire slice. And so the fact that we can write the entanglement entropy of these non-local sources as entanglement entropy associated with local sources means that you couldn't get entanglement entropy on the previous slide. This effective local source can be defined implicitly in terms of a derivative of this W that was our sources, which I've just rewritten here. The argument for this has two parts. One is to show that the one-point function in the non-local source background can be written as the variation of some partition function of the local sources. And then there's a second bit that's perhaps a little bit more technical, that the partition function and the entanglement entropy equations themselves have extra terms that are going to cancel out. So it's the first part of this argument can be made with a pretty simple diagrammatic argument. To start, we can write the, or at least diagrammatically, we can write the one-point function of the operator O in the effective lambda effective background The black dot is going to be the O itself that I'm taking the expectation value of. And then this red dot with a black outline is going to be the effective source. And so the 1-point function is just given by the 2-point correlator, 3-point correlator, 4-point correlator, 5-point correlator, so on and so forth, sourced by this effective source. Now, if I choose to define the effective source implicitly in terms of, as I've written down here, so it's going to be just the original local source plus the bilocal source connected to correlators of all sizes with effective sources on the ends, plus the trilocal source with all correlators connected to effective sources. You can see that by applying this definition of the effective source up to the thing above, recursively, you can build any tree that you want connected to this black dot. And because the solution for the 1-point function in the non-local source case is the black dot connected to any tree, this definition of the effective source shows that the 1-point function of lambda effective is equal to the 1-point function of O in the non-local source background. But looking at this line closer, everything past the bilocal source is just the original O lambda effective up here. And so I can replace the sum that I did down here, that I did down for the effective source, with just a things that where each bilocal source and trilocal source connects to the effective source, or the 1-point function of the effective source in the 1-point function of O in the effective source background. This sum on the right-hand side here is just stripping one O off of omega. Sorry, not omega, W. So the sum that I've written here is exactly the thing that I wrote 2 slides ago for the definition of lambda effective. Because the 1-point function of O in the non-local source background is equal to the variation of the partition function with respect to lambda 1. We have this relationship. These two are equal by what we've just argued, and so there's an equality between this partition function of lambda effective varied with respect to lambda effective, and the partition function of the non-local sources varied with respect to the original lambda 1 in the non-local source case. So the fact that the variations are equal does not mean that the partition functions themselves are equal, and in fact they're not. The relationship is maybe a little messy. The details are not that important. This is actually very easy to check by just taking this relationship between the two partition functions, varying it respect to lambda 1, and then using the fact that we know lambda effective in terms of lambda 1, and we know a log z in terms of lambda 1 to check that using the results in the previous slide and taking the variation of this respect to lambda 1, you can check this very easily. Now the entanglement entropy is given by log zn minus n log z1. But there's an extra complication, which is, well, so what we want to do is take this form for log z and plug it into the entanglement entropy and see what we get. There's an extra complication that comes from the fact that lambda effective as defined actually depends explicitly on the replicant number, because it depends on correlators that run off to non-local sources that may be on other replicas. And so if we calculate the entanglement entropy using this effective partition function, we pick up an extra term that is just the chain rule. There's the variation of z effective with respect to lambda effective gives you the 1-point function, and then there's this explicit dependence of lambda effective on dn. We can figure that out by just applying it to the definition of lambda effective, and you can check that if you take this and plug it in here, it exactly cancels the replica derivative of this extra term that we've found between the two partition functions. So what we end up getting is that there's the statement that I made originally, which is that the entanglement entropy of the density matrix in this non-local source state is equal to the entanglement entropy of this different density matrix given only by these effective local sources, two leading order and n. So a couple comments on this. One is that the non-local sources are able to change the entanglement order, the entanglement entropy at leading order and n, but only in a way that's equivalent to adding local sources. Without a local source at all, so when lambda 1, the original lambda 1 is 0, you actually don't get any change to the entanglement entropy at leading order in n at all. And this is easy to see because the contributions to the entanglement entropy are trees, or the contributions to the n squared entanglement entropy are trees, and you can't have trees if you don't have n nodes. You could only get loops. There's no non-trivial bulk entanglement entropy in the fields in these states, simply because, sorry, I'm blanking. Oh, right. The ability to write any non-local set of insertions as a local source effectively, and we know the local sources correspond to coherent states that don't have bulk entanglement entropy, and so the non-local sources at leading order can't either. Something to point out is that this thing that I've gone through is a non-local CFT only version of Witten's argument for how to handle boundary conditions in ADS CFT for multi-trace deformations. The effective source is effectively the leading fall off the source in his story. And it is equal to the derivative of the deformation with respect to the 1-point function, which is the subleading source. So that matches with what he did. And then finally, just to suggest that this is maybe not, well, there's something special about the entanglement entropy, is that if you attempt to do the same thing for the Rene entropies at leading order, you will find that the effective source, Rene entropy, and the non-local sources do not match. So the Rene entropies are a little bit more sensitive to the details of the state, and the entanglement entropy is not picking up the difference between this effective source and the non-local sources. All right, so we can't really, I guess we were after bulk entanglement entropy in the fields. We can't get that at n squared. So the thing to do is to move on to the next order down in n. In the diagrammatic picture, this has to come from loops, from the arguments before. And so from now on, I'm going to simplify things by first removing the local sources entirely, so there's no n squared contribution. The kind of leading order is n0 now. And only consider bilocal non-local sources just for simplicity. And as a warm-up, we can again consider the entanglement entropy of a mixed state, so a bilocal source that couples the lower half to the upper half. And we consider the full entanglement entropy. So look at the region is the entire spatial slice of the CFT. In this case, it's fairly easy to write what the density matrix is in a perturbative expansion to, I guess, first order in lambda 2. There's the normalization, but it's just going to be the vacuum. And this really is the vacuum because it's not a thermal state because the region of interest is the entire CFT. Plus a perturbation that has 1O on the left and 1O on the right. And it's possible to take this row and this density matrix and solve for the entanglement entropy directly using the replica trick. You can sort of see what the answer is. You can sort of posit just by looking at this what the answer is going to be. It goes into rho log rho. Anything that is made up entirely of vacuum states is going to give 0 because the density matrix or the entanglement entropy of the vacuum is 0. Anything that involves some of the perturbation and some of the vacuum is going to vanish because the one-point functions vanish. And so the leading contribution is going to essentially be the second contribution, the deformation log the deformation. And this is the answer that you end up getting. If you treat, the entanglement entropy is trace A log A, where A is a thing that we're treating as a matrix as far as the log is concerned, which is this kind of integral of 1 lambda 2 and 1 correlator. And the key point to take away from this is that the entanglement entropy is non-analytic in the source at this order. So the kind of leading order contribution to the entanglement entropy goes as lambda log lambda. We can kind of, in a hand-wavy way, motivate how this occurs from the replica trick.
So this is very interesting, right? I mean, this is something that I probably wouldn't expect.
Yeah, we were a little surprised by this. Now, so I will, well, sorry, if you had a specific question, ask it, but I was going to go on about.
No, I was just expecting that there's maybe some reformation that underlies this, but maybe this is what you want to show.
Well, yeah, so I think what we're going to try to argue is that when we go and do this for kind of a real system, one where we're not looking at the whole CFT as the region, we find that various perturbations diverge. And so the suggestion is that this thing that includes non-analytic terms in lambda is the resummation of that, although we can't do it in the real case explicitly. And so I guess these little examples are going to try to motivate that something like that happens. And now it's not entirely unreasonable for a reason that I'll say in a 2 slides, I think. There is something kind of physical that kind of may fail about the perturbation theory. But to just hand wave real quick how this occurs from the replica picture, there are kind of 2 types of contributions to the entanglement entropy on the N replicas. One that you might call contractible diagrams, and these consist of loops that don't depend on the replica number. This one sits on just 2 replicas, and if I add 5 or 10 more replicas, it doesn't care. Alternatively, there are non-contractible diagrams, and these are ones that kind of wrap around the replica, the set of replicas. And so these kind of necessarily, the power of lambda 2 depends on the replica number. And for a given replica number, for like n equals 4, these 2 diagrams are going to look like they're the same. But when you do the analytic continuation and take a derivative with respect to n, as you need to do to get the actual entanglement entropy, the contractible diagrams are going to give analytic terms, while if you take the n derivative of this thing, you'll see that you'll get a log lambda out. And so this is kind of our understanding from the replica picture where these things come from. To kind of argue, and maybe this is the point that I said I was going to make 2 slides back, is that to argue that this non-analytic behavior makes sense, we're applying a perturbation that is a kind of infinite matrix to a density matrix that is also an infinite matrix. And if our perturbation eigenvalues shrink slower than the unperturbed eigenvalues, then it's possible that no matter how small we make our perturbation parameter, there's going to be at some point where things blow up. And in the toy example where things were the vacuum, it's kind of real obvious that it can happen there because the vacuum density matrix is not full rank. And so if the perturbation has any eigenvalues where the vacuum has 0 eigenvalues, it doesn't matter how small you make the perturbation parameter, the perturbation could fail. And so as a kind of quick little example, you can consider a single harmonic oscillator in a thermal state. And our perturbation is going to be a perturbation to a higher temperature, a slightly higher temperature. You can just take this perturbed density matrix and plug it into the equation for the entanglement entropy. Everything's exactly solvable because it's all diagonal. And there's a term in that entanglement entropy that goes as this sum that I've written here. And the sum is manifestly finite because the exponential suppresses anything that the log produces. But if you try to expand the logarithm order by order in lambda, it's guaranteed to diverge at some point once you've gotten up to expansion parameter k equals beta over a. And in addition, you can actually solve this sum in good approximation by treating it as an integral. And you will indeed find that the solution to this sum has log lambda terms in it. So our assumption is that we're getting behavior like this in the calculation of the entanglement entropy. And so what we expect in a kind of order by order perturbation in lambda is that we are going to eventually see divergences for some set of parameter space in lambda. And so the next thing to do is to go see if we can see that. And to do that, I'm going to switch to a different way of calculating the entanglement entropy. So instead of using the replica trick, I'm going to write or think of the entanglement entropy as the expectation value of the modular Hamiltonian. I just rewrite the perturbation of the density matrix in a slightly different way. We call this the bare perturbation, where we've stripped off some Euclidean evolution. And it turns out, given a particular bare perturbation to a density matrix, it's possible to write the perturbation to the modular Hamiltonian in this integral form. Which it boils down to an integral, a kind of non-commutative integral expression for a logarithm. These kernels, k sub k, are known explicitly, but we don't. It's not going to matter what they are exactly. What matters is going to be where their poles are. And so they have poles at the first and last s have poles at 2 pi in for integer n. And then there are poles anytime an s encounters in the imaginary direction another s. And so what these s's do, if you look at the term over here that involves the perturbation, is that they flow the perturbation for any amount of real time that you integrate over all real s. And then for a fixed amount of imaginary time based on where we've chosen the contours of Sj. All right, so we want to take this delta k and throw it into the expectation value and ask when it diverges or doesn't. And so schematically, a particular kth correct or contribution to the entanglement entropy is going to look like many of these bare perturbations with their different s's flowed by different amounts, all on an expectation value. We can solve this by introducing a whole bunch of resolutions of the identity, but any given resolution is going to diverge if the thing that's on the inside scales positively with Euclidean time. So if it runs as e to the positive vacuum modular Hamiltonian or thermal modular Hamiltonian, then that particular integral will diverge. And so to avoid that happening, what you want to do is essentially Euclidean time order all of these these flowed delta rho b's. because it kind of in each resolution of the identity, you have to be farther back in Euclidean time so that you're always kind of having e to the negative some k. And so the question now is, we have freedom to pick how much these things are flowed by in imaginary time by deforming the contours up to the fact that we can't cross any of the poles. And so the question is, are we able to actually perform this deformation to get what we want? And the answer is, for local sources, yes, we can. In order to avoid them crossing, a simple prescription is to say that all the SJs have to lie between 0 and 2 pi, because that's where the poles at the ends ones are. And then to avoid them crossing each other, each next one has to be greater than the one before it. If I start with some delta rho b's that are organized in some disorganized way in Euclidean time, I can always find arrows shorter than 2 pi that shift them into a ordered sense, into something that's ordered in time, where each arrow is shorter than the next one. So it's always possible, given local delta rho b's, to come up with a kind of defined convergent answer to the entanglement entropy. However, if the delta rho b's are non-local, then we may or may not actually be able to accomplish this. So if they have small finite extent in imaginary time, then it's still possible to find an arrow that puts one that's in the wrong place in proper Euclidean time order. But if the finite extent is really large, even the largest possible thing that we can pick for the contour, which is going to be 2 pi I, is not going to prevent them from being out of order in a particular place. And so these non-local sources are capable of producing things that kind of necessarily diverge. In particular, the requirement is real simple. If the total finite in imaginary time extent of all of our perturbations are greater than 2 pi, then that particular term in the entanglement entropy diverges. And in particular, for any non-local term, this will occur at some order in k, because as long as it has any finite extent, I just have to pick k equal to 2 pi over that finite extent, and I'll have found the term that diverges. Just to show that we can do this a little bit more explicitly, and that these divergences really kind of occur in the numbers, let's pick a specific example. If the bilocal source is some small perturbative number times insertions at just spatially at the origin, but one insertion's back at minus a over 2 and the other insertion's at positive a over 2, the spatial extent of this lambda 2 is a. I can calculate the second order contribution in lambda, so lambda 2 squared to the, what's actually the relative entropy here. It just saves us one term to calculate the relative entropy instead of the actual entropy, but the rules work out the same. I get something that looks like this. And if I pick a kind of, right, so sorry, to leading order in n, which in this case is n to the 0, not n squared, I can factor this 4-point function into 2-point functions. And if I assume the 2-point function has some kind of normal free thermal 2-point function, then I can calculate this explicitly for certain values of delta. And we do indeed find that this contribution to the entanglement entropy diverges exactly as a goes to pi, which is the point where when you have two lambdas, their finite extent is beyond 2 pi. The divergence in the right. So I guess what we're expecting is that these divergences in the relative entropy and in the entropy, if we could do the resummation, would resum to something like that lambda log lambda that we saw in the simple toy case. So a couple comments on this. One is that we aren't the first to see these divergences. Gabor Sorosi and Tomonori Ugejin saw these divergences in what was a similar context when they were studying excited states that were not these perturbative excited states, but a different set of excited states. Two, we expect this non-analytic behavior to be present in the bulk entanglement entropy as well. Just because well, I suppose there's a number of different ways to say it. One way that I'll maybe talk a little bit more later is that there's the statement that the bulk relative entropy is expected to be equal to the boundary relative entropy. And so given that we saw a divergence, a non-analytic behavior in the CFT relative entropy, I would expect a similar thing in the bulk. And so in principle, this could be something that could be, you could go looking for in the bulk calculation. And then a kind of maybe side statement that I don't entirely know the interpretation of is that we expect the divergence actually occurs for local sources too, if you look to high enough order, which in this case is going to have to be fourth order in the source. Although we couldn't really study this directly, it was harder. And what happens here is that if you take the density matrix associated with the local source and just expand it, not to first order in lambda, but to second order in lambda, the delta rho b, the perturbation to the density matrix at second order, has finite extent between these two lambdas in the same way that the non-local source did. So I'm not really sure what to make of that, but it seems to be the case that even the local sources diverge in this sense if you are asking sufficiently higher order questions. Okay, so I'm mostly out of time, so I think I may give a more executive summary of this last section. This geometry from entanglement program was our original motivation, but we didn't really succeed at accomplishing what we wanted. So this is really going to be more the setup of a problem than it is going to be any actual solution to anything. Geometry from entanglement entropy, what we really want to do is take the something I'm calling the perturbative quantum Ryu-Takayanagi formula, which is really just FLM, where I've wrapped the area term in an expectation value to remind people that it's an operator. And then everything is kind of perturbative in some lambda near the vacuum. What we want to do is we want to show, what we would like to be able to show is that if this thing that I've called QRT is equal to 0, which amounts to FLM holding, is that this implies that there's something that you would call a perturbative quantum version of the bulk equations of motion holding in the bulk. And so I'm going to start by basically just saying a bunch of applying a bunch of tautologies to this QRT to reorganize terms to make things look a little bit more like what we would maybe want them to look like.
Sorry, just to make sure I understand the notation. So the area with a hat is supposed to be somehow a contribution to the bulk entanglement entropy having to do with gravitons, and then like the S bulk is like whatever other matter fields you have and their contributions.
I think you could split it up that way. What it really comes down to, I think, is that the division between these two things is not well defined, because what I'm imagining here is some unspecified operator in quantum gravity that gives you the area when you act it on states that you know how to calculate the area in, and does really no one knows what on other states. And in that way of talking about things, entanglement entropy in the gravitons that is kind of low level and perturbative could still be in S bulk. But there's kind of I think there's a freedom to kind of shift things between these two terms. So I'm not. I'm going to kind of avoid making an extremely definitive statement.
And to what extent the area operator is not just the modular Hamiltonian of a region?
Sorry.
Aside from the fact that, because I mean, like, this is something that gives you the area, it's like in the leading order when you calculate the expectation value. Aside from the fact that it's not really like an operator, like state-independent operator in quantum mechanics.
Right. Sorry. Sorry. Maybe I lost track of the question. The area operator, or at least the way I'm kind of used to from some stuff that like Aitor, I'm forgetting which collaborator of his was the one for this, but that oh, right, sorry, this is just from JLMS, that the CFT modular Hamiltonian and the bulk modular Hamiltonian are related as kind of as operators by these local area terms, and so they're kind of two different ways of measuring the modular Hamiltonian. That's not really saying that the area term is itself a modular Hamiltonian. Maybe I thought that's what I heard you say, but maybe.
No, I was just talking about the expectation value. No, but let's move on. I mean, I think you.
Yeah, like this is. I'm not even sure speculative is the right word. We're just trying to organize terms that we have not well defined. Like I will admit entirely that it's maybe not very well defined. So yeah, okay. I'm now over time, so I'm gonna give a kind of quick summary of this because it's kind of head wavy anyway. We can apply two very quick things just via the definition of the relative entropy. We can split the entropy up into the expectation value of the vacuum modular Hamiltonian and the relative entropy. When the region has a killing symmetry, which is true for the vacuum on ball-shaped regions, the modular Hamiltonian can be written as the integral over the local stress tensor. And we can apply both of these formulas to both the bulk and the boundary CFT to get a much more complicated version of this QRT. On the next page, I've rewritten the same thing that I had on the previous page, where I've grouped terms suggestively and added and subtracted this expectation value of E grav. And the E grav is simply defined by the it's the holographic bulk energy. It's defined by the leading order H metric field out at the boundary in Pfefferman-Graham coordinates. And so at this stage, we could say that from JLMS that RE, that the thing that I've called RE, which is that the bulk and boundary relative entropies are equal. I'll say leading order. And then second, ST equals 0 is given just by the holographic dictionary. The idea that the CFT, the expectation value of the CFT is equal to this, the stress tensor in the CFT is equal to the value of the metric out in ADS. And actually, if you take these RT formula kind of small, like if you take very infinitesimal ball-shaped regions, all these other terms fall out. You can actually get ST equals 0 just from RT. Classically, so what we want to deal with now is deal with the remaining terms. Classically, there's an energy associated with ball-shaped region that can be written in terms of E grav, the area, and the bulk equations of motion. And this energy is equal to the integral of the bulk stress tensor over the region. Oh, that's an error. That should be a sigma, not an A tilde here. The region that you're integrating over is the whole bulk region, not just the boundary where the area is calculated. And there's an argument by Hollins and Wald using the reparameterization, the symmetry associated with the reparameterization invariance in gravity that says that this quantity vanishes classically. This whole thing, it says the same statement that these are equal to each other. The whole thing, this minus that vanishes. There's a whole calculation behind that, but it's essentially like a Gauss's law constraint for the reparameterization variance. The egrav is the contribution at one boundary, the area is the contribution at the other boundary, the energy is the source in the middle, and then for those to all actually cancel out correctly, the equations of motion that propagate one to the other have to hold. So by applying all of this, we can reorganize QRT into something that's has a bunch of different terms. And classically, each one of these, REST, KH, which is, and this thing that I've called Hollands-Wald, they all vanish independently. And so that gives you that RT equaling 0 implies that the only thing that's left over, this integral over the equations of motion. If RT is equal to 0, then the equations of motion also vanish as appropriate. And so what we would like to do is kind of posit quantum mechanical versions of KH equaling 0 and HW equaling 0. I think the other two are better understood. To get something like QRT equals 0 implies that some expectation value of the equations of motion is 0. We can't really get much farther than positing it, and it's entirely possible that there are more complicated cancellations that cause FLM or RT to hold so that each of these don't vanish independently, but they kind of vanish together. We tried to get a handle on this, but didn't really succeed. One kind of trivial example I can tell you about is that if you consider bilocal scalar sources, these kind of non-local sources I was talking about for most of the talk, and think about only linear terms in the bulk metric, to leading order, which is now n to the 0, because the bilocal scalar source only sources things at n to the 0. You can write the expectation value of the metric as a sum over one interaction with the scalar field, and then any number, there's going to be one loop for n equals 0, but there's going to be a sum over terms where there's any number of lambdas in here. And so this is a case where we have kind of quantum mechanical scalar matter sourcing the bulk. But it's not very interesting because the linear order, the expectation value of H just acts like the classical value of H. So KH equaling, like all the things that we wanted to study kind of inherit trivially from the classical formula. And so so what we've really just recovered is that it's a kind of explicit construction of a semiclassical gravity equations of motion, where the gravity part is acting classically, and we have some sort of quantum matter. What we would really need to go farther than that would be something that some part of the expansion where you kind of have H hat squared, and we couldn't come up with a good way to define any of that. So I think there are kind of still issues with defining some of this, but we were hoping that these non-local sources would give you some handle on at least perturbative bulk fields in the bulk. All right, so just to conclude real quick, what we've done is we've built perturbative states with non-local multi-trace sources in a CFT Euclidean path integral. The bulk state has non-trivial entanglement in the fields. That entanglement entropy is kind of necessarily order n to 0 or lower. Non-local sources can change perturbative, the CFT entanglement entropy at order n squared, but it can't create it. You need local sources in there. to create it. And the new entanglement entropy matched that of a different local effective source. Maybe the most interesting thing is that there are these non-analyticities in the order n to the 0 non-analytic sort. There's these non-analyticities in the entanglement entropy at order n to the 0. And it leads to divergences in the perturbative expansion. And we expect that this will show up in bulk fields as well. And then there was this kind of attempt at organizing the quantum RT formula to be kind of suggestive of what we would want to find if we were trying to pursue this, geometry from entanglement program. And what we expect or hope is that some kind of perturbative quantum version of Hollands-Wald holds. Just a couple things on future directions. There was a paper by Bell and Iqbal and Lacan where they check FLM explicitly using non-perturbative a non-perturbative single trace state, a single particle state. So not this thing that's kind of near the vacuum. Because it's not perturbative, in order to have control over the calculation, they need to use a small interval approximation. But in that small interval approximation, they can explicitly check that FLM holds. And in principle, we could extend their results to our states, and we wouldn't need the small interval approximation because we kind of have perturbative control in a different way. So this could possibly give their results in a different, or check FLM in a different regime than what they did. And then second, this kind of Hollands-Wald formula, which was the thing that was hard to define in the bulk, it arises from this reparameterization symmetry, and you might imagine that the thing that we're hunting for you could get through a careful treatment of ward identities, but we weren't quite sure how to make it work. So maybe that would be something that could be pursued as well. So thank you very much. I think I should stop.
Okay, thank you. Okay. So we already had some questions. Are there further questions from other people online? Maybe let me ask. In the beginning, you mentioned that local sources do not change the entanglement entropy, right? Local sources.
They don't change the. They don't change the sorry, they can change the CFT entanglement entropy. They don't change the bulk entanglement entropy to leading order. So the well. When I say bulk entanglement entropy, I mean the entanglement entropy of the fields in the bulk on the background. They can change very slightly the area of the surface, and that corresponds to the change in entanglement entropy you see in the CFT.
So that's already in the holographic picture with the area that, as you argued.
Right.
Okay.
So Right. So the statement is not that they can't change the entanglement entropy of the CFT, because they can do that. It's that the bulk fields are coherent states, and so to leading order, they don't see a change in their entanglement entropy, but the area of the surface can.
I actually have a question. So can you hear me?
Yes.
Yeah. Okay. So what do you think, like where this field of exploring the relation between action equations and entanglement entropy is going, in a sense that to what extent the stuff that he told us about is based on some universalities in correlation functions? I remember that, deriving Einstein's equations from entanglement first law, like what you may argue for it, like using basically the conformal symmetry, and you can derive like quadratic corrections to this using universality of 2-point functions of the stress tensor, right?
Mm-hmm.
So what is your feeling where you're going?
Yeah. So So the kind of earlier things in that were so specific. Or sorry, they were so universal that you didn't even need infinite n to make any statements about them, because they depended, as you said, only on they depended only on structures of the 2-point functions, and the 2-point functions are completely fixed by symmetry. Now, while I guess the symmetries are still very useful in the calculations. Some of those extensions, such as especially the one that involved higher derivative terms, you start to need more and more data about the CFT as you say those things. So the second order calculation actually requires one extra bit of information about the CFT. I think it's the ratio of like how you normalize the 2-point function to some other invariant or something. It's something like I don't remember immediately. But then when you go and look at higher derivative corrections, you need more and more kind of information about the CFT. So it feels as if, to me, that there has at least been some success in pushing the results away from things that are maybe so obvious from universality that they kind of have to be true. That said, I think the sort of stuff we were trying to do here would be the most interesting way to push that away, kind of push that forward, where you're starting to really have to worry about the details of the quantum fields in the bulk. And we didn't succeed, and we're finding it very hard to define things. So I would be willing to believe that it would be tough to push it much farther forward, but yeah, maybe there's something that can still be done.
Okay, thanks.
Okay, there are no further questions. Then let's thank the speaker again.
Thank you, and thank you also for making the effort.